Hello guys, welcome to this video. So in today's video, we're just going to cover like how can we actually apply CAN matrix on a real life situation. So I'm an engineer and I deal with a lot of circuits and so on. So I really wanted to really find a way to actually apply the CAN network in a real life situation. So I decided to see the kind of equations I can come up with which are related to what I do electrical systems, which I'm a bit familiar with. So I decided to use this equation, the inductor equation, where I, the inductive voltage is directly proportional to the rate of change of current, and the L, which is the impedance, how much magnetic field this inductor can store. Okay, so the more current that flows through the inductor and the higher the constant, the more energy or voltage this inductor can store. So it actually depends on the time and the current as well as the inductance, which is L. So this is the symbol of an inductor in an electric circuit. Okay, so we're going to dive into how we can actually now try to simulate the behavior of an inductor using the GAN network. So first we're going to generate the data. The inductor H is held constant, the simulating current through the inductor. So we're going to use a solenoid current to flow through the inductor. These are the time points. L is held constant, and the resistance is also held constant. So when we pass the points in the sine function, we are able to generate different current flows with different points in time. So the gradient will actually do the differentiation for us. We don't have to do anything. Then it's going to print out the time and at which what was the current at that time. So at 0.01 second, the current was this, and the current kept on increasing depending on the time, and it fluctuates because it's a sine wave like this. So the current is always going to change in proportional to the time at which the current is flowing. Okay, so I generated the data and I stored it in the form of a CSV file. So I iterated the information 5,000 times so that it can actually generate enough data we can use to actually train the cans and see the type of equation it's going to come out and see if it's applicable or it's going to simulate the same behavior as um, the original equation above. Okay, so this is the data that came out. We have the time, we have the current, we have the change of rate of current and the inductive voltage. So I installed the GANs, which you can actually get from their official site or the official GitHub repo. The guys that wrote the paper, you can actually read through the paper to actually have a good intuitive understanding of how cans can actually be used. I'm going to attach links below in the description where you can go through my GitHub repo and see how these things are applied and go through the paper. When the data now is being preprocessed, we form the input data, which is X, so the time, current, and the rate of change of current. Then the inductor voltage is our output. Okay, we split the data and we turn the data into tensors. Okay, we're going to turn the data into tensors, so some of it is going to be for the training set and the other for the testing set. So this is the output and the sizes of the data. It has got 500 rows and so on. Okay, then we can also plot how this data is going to appear. So we have training and the labeled data, which is in form of a sine wave. Okay. Then the first thing we'll initialize the can, which is a 3 to 1. Okay. So this is the first um, equations is going to form. So it's like you have this amount of data and you want to get experimental data. Maybe you are experimenting. This is how an inductor is behaving, and you want to come up with an underlying equation that governs how the inductor is producing, how much energy the inductor is producing. So we choose 3. So 3 is for the three-dimensional inputs. 1 is for the output. But K for the spline and 3 for the grid, how deep the neural network is going to be. Then the model is fed with the training data. We plot the first functions. So this one looks like a linear function, an exponential function. This function, I don't know it so very well, but can print the function out. Then we start training the cans. So one advantage of the cans is that you can keep training them in band sizes. Then you can prowl them so that you can reduce the size of these models. Okay, I'm using this as the optimizer and the steps in which it can build these CAN networks. Okay, so I did the training, then fixing activation functions. So we have to fix these activation functions after training. We're supposed to fix them. So I supplied with a library of different functions. Then it's going to fix them based on their behavior. So it fixed them, and this is the equation that came out. I assessed the model's accuracy. It's around 4.71. That's the accuracy of these models. Then testing the equation with the actual values from the CSV file. So I tested it with several rows, but I got the row on 496.9. That's the row I got to test this model. Then this is the final answer, and it's very close to the actual value within 2 decimal places. It's not very accurate, but you can see the results. It's able to actually simulate the behavior. It's very, very close. I also did some measurements where I measured the error between the measured value and the actual value. So it's going to be really, really small, which is negative 0.3, which is a good thing, meaning it's not a 100% error free. It's not very accurate. I can do some more training, but for this video, I just wanted to show you like how you can apply these neural networks in a real life application. And this is what I had for you. Please subscribe. And if you've got any questions, drop it in the comment box. If there are any clarifications, I would really like to assist wherever I can. Every data is on my GitHub where you can read, where I added some more notes where you can read through, and this notebook is also open source. You can go through to really understand. You can also read the paper so that you can actually have an in-depth knowledge of these new neural networks. So thank you guys. Until next time.